Our galaxy holds billions of worlds beyond our solar system. The greatest scientific quest of our time is to find which ones might be home to life. By the end of this exploration, you will know the 30 most promising exoplanets where we could find our cosmic neighbors. We will journey to planets with global oceans beneath pink skies, to super-Earths gripped by eternal dawn, and to mysterious worlds where the air itself hints at biology. What does it feel like to stand on the shore of possibility? Just 4.2 light-years away, a world orbits our nearest stellar neighbor. Proxima-Centauri-b is a rocky planet, roughly the same size as Earth, and it sits in the star's habitable zone, that temperate band where temperatures might allow for liquid water to exist on the surface. This discovery, made in 2016, sent a wave of excitement through the scientific community. We had found a potentially Earth-like world right next door. But life on Proxima-Centauri-b would face extraordinary challenges. Its sun is a red dwarf, a small, cool, but notoriously temperamental star. Red dwarfs are prone to violent outbursts called stellar flares, which can blast a nearby planet with intense radiation, potentially stripping away any atmosphere and scouring the surface. This raises a critical question. Could Proxima-Centauri-b hold onto a protective blanket of air? Some models suggest a thick atmosphere or a strong magnetic field could shield the planet, creating pockets of habitability. Others paint a bleaker picture of a barren, irradiated rock. The debate centers on whether this world is a temperate oasis or a cosmic desert, yet the possibility remains tantalizing. If it has an atmosphere and water, its surface conditions could be surprisingly stable. The planet is tidally locked, meaning one side faces perpetual daylight while the other is locked in eternal night. This creates a stark world of extremes, but along the thin line of twilight between them, the terminator zone, conditions might be just right. Here, a visitor might stand under a dim, crimson sky, looking up at a star 3 times larger than our sun appears, but far dimmer and redder. The search for answers continues, with astronomers using the most powerful telescopes to hunt for signs of an atmosphere. Proxima-Centauri-b is our first stop, a reminder that the frontier of life may be closer than we ever dreamed, yet profoundly alien. The possibility of a twilight world is just the beginning. An even more remarkable planetary family awaits us 40 light-years away, orbiting a star so faint it would appear no brighter than Venus from the surface of its worlds. This is the TRAPPIST-1 system, a cosmic marvel where 7 Earth-sized planets dance in an orbit tighter than Mercury's path around our Sun. At the heart of this compact family, the 4th planet from its dim red sun, shines the most promising candidate of all, TRAPPIST-1e. This world is often called the crown jewel of the system, a rocky planet with a density almost identical to Earth's, sitting squarely in the middle of its star's habitable zone. The conditions here could allow for vast oceans of liquid water to cover its surface, a true water world suspended in perpetual twilight. Scientists believe it could possess a thick, nurturing atmosphere, one that might efficiently redistribute the star's gentle heat around the globe, tempering the extremes of its likely tidally locked rotation. Standing on its surface, the sky would be a deep, dusky red, and the view would be unlike anything in our solar system. The other planets in this intimate system would appear not as distant points of light, but as large, distinct orbs hanging in the sky, some seeming even larger than our own moon. You could watch your neighboring worlds transit the face of their star, their silhouettes drifting across a crimson disk. This incredible system is a prime target for the James-Webb Space Telescope, which is now analyzing the starlight filtering through these planets' atmospheres, hunting for the chemical fingerprints of water vapor, carbon dioxide, and perhaps even hints of gases that should not exist without biology. TRAPPIST-1e represents a new paradigm, not a lonely oasis, but one world in a bustling archipelago where the search for life has 7 chances to succeed. While the TRAPPIST-1 system shows us a family of worlds, another discovery proved a single, profound point. In 2014, the Kepler telescope confirmed the existence of a distant world called Kepler-186f. This was a landmark moment, the first time we had ever found an Earth-sized planet orbiting comfortably within the habitable zone of another star. Before this, we knew of larger, puffier worlds in that temperate band, but Kepler-186f was different. It was a signal, a cosmic announcement that planets like our own were not rare flukes, but likely common throughout the galaxy. This world circles a star that is cooler and redder than our Sun, a red dwarf much like Proxima-Centauri. Its orbit is tighter than Earth's, taking only about 130 days to complete a year, but because its star is so dim, it receives only about a third of the stellar energy we do. Standing on its surface, the daylight would feel like the golden hour just before sunset on Earth, but that light would be tinted a deep, ruddy crimson. This has led scientists to wonder, if plant life evolved there, what color would it be? On Earth, plants are green because they use chlorophyll to absorb the red and blue parts of our Sun's white light, reflecting the green. Under the perpetual crimson glow of Kepler-186f's Sun, evolution might favor a different strategy. Alien vegetation could be black to absorb every precious photon of that dim red light, or perhaps a shade of purple or even infrared, colors our eyes could not perceive. The planet itself is only about 10% larger than Earth, and its calculated density strongly suggests a rocky composition, another key ingredient for Earth-like life. We do not yet know if it has an atmosphere or oceans, but its very existence shifted the goalposts of our search. Kepler-186f was the proof of concept, the first clear evidence that the universe builds planets in our size range and places them in the Goldilocks zone. It transformed the question from "Are there other Earths?" to "How many are out there and what are they like?" This single point of red-tinged light 500 light-years away opened the door to everything that followed. Kepler-452b is a world that feels hauntingly familiar. Discovered in 2015, it orbits a star almost a perfect twin to our own Sun, a yellow dwarf of the same temperature and size. Even more compelling, it completes a full orbit in 385 days, a year just 20 days longer than ours, and it sits in that star's habitable zone in a nearly identical position to Earth. This is not just another exoplanet, this is Earth's older, larger cousin, a super-Earth about 60% bigger than our home. Standing on its surface, the sky would look strikingly similar, lit by a sun you would struggle to tell apart from our own. But the experience of being there would be profoundly different. That increased size comes with a much greater mass, meaning the pull of gravity would be at least twice as strong as what we feel on Earth. A simple walk would become a strenuous hike, and the flight of any bird-like creature would require immense strength or radically different anatomy. The atmosphere, if it exists, would likely be thicker and denser, trapping more heat and potentially creating a runaway greenhouse effect. Yet the most awe-inspiring detail is not its size but its age. The Kepler-452 system is around 6 billion years old, making it 1.5 billion years older than our solar system. That is an additional 1.5 billion years for life to arise, evolve, and complexify. If life began on Kepler-452b at a similar point as it did on Earth, it has had an unimaginable head start. What could evolve in that vast expanse of extra time? While we might imagine a planet long ago consumed by its own star, Kepler-452's sun-like nature means it has been stable, offering a consistent, nurturing light for eons. This presents a staggering possibility. If civilization emerged there, it could be millions of years more advanced than our own. Their technology, their understanding of the universe, their very existence could be beyond our comprehension. Kepler-452b whispers a tantalizing question across the 1,400 light-years that separate us. In the deep time of the cosmos, what is the ultimate destiny of a living world? But the search for life demands more than just a promising location. It requires the right ingredients, a chemical recipe for a living world. 49 light-years away, orbiting a quiet, stable red dwarf star, a planet named LHS 1140b might be setting that cosmic table. This is not a twin of Earth, but something more massive and mysterious, a super-Earth with over 6 times our planet's mass. That extraordinary heft creates two fascinating possibilities. LHS 1140b could be a rocky world, but one so dense and heavy it would be covered by a global, planet-wide ocean hundreds of miles deep, a true water world. Alternatively, it might be a mini Neptune, a gaseous world with a thick, deep atmosphere shrouding a smaller, possibly rocky core. For years, astronomers debated which version of this distant world was real. The answer matters immensely because a global ocean or a thick atmosphere could both, in theory, cradle life. Its star is a crucial advantage, a red dwarf that is unusually calm and old, having long ago settled past its violent flaring youth. This serenity gives LHS 1140b a far better chance of holding onto a protective atmosphere, a stable blanket that could nurture chemistry over billions of years. Then, in 2024, new data from the James-Webb Space Telescope offered a stunning clue. By analyzing the starlight filtered through the planet's atmosphere during a transit, Webb's instruments detected hints of a nitrogen-rich air. Nitrogen is the silent, stable background gas of our own atmosphere, making up 78% of the air we breathe. It is not fuel for life by itself, but it is a crucial stabilizer, a diluting agent that prevents oxygen from becoming too reactive. Finding it in abundance on another world is like discovering a planet has built the foundational canvas upon which the painting of biology could be drawn. This tentative detection points toward the mini Neptune scenario, a world with a deep, dense atmosphere where complex organic molecules could form in the skies or rain down onto a hidden surface. LHS 1140b, with its great mass and potentially nitrogen-rich skies, reminds us that the formula for a living world may come in many different sizes, some far grander and more imposing than our own pale blue dot. That deep, stable atmosphere of LHS 1140b is a precious commodity, especially around a red dwarf. But 12 light-years away, another red dwarf system holds a world that feels even more like home on paper. Teagardens Star B doesn't just orbit in the habitable zone, it ranks as one of the most Earth-like planets we have ever found. Astronomers measure this similarity with a tool called the Earth Similarity Index, or ESI. It is a simple scale from 0 to 1, where Earth scores a perfect 1.0. The index compares a planet's size, density, surface temperature, and escape velocity to our own worlds. A score above 0.8 is considered very Earth-like. Teagardens Star B scores an impressive 0.95, one of the highest values ever calculated. This is because its mass is almost identical to Earth's, and the amount of starlight it receives, its insolation, is strikingly similar to ours. If you could stand on its surface, the warmth from its dim, ultra-cool red dwarf sun on your skin would feel very much like a sunny day here. But that is where the familiar comforts end. This planet is almost certainly tidally locked. One hemisphere is a land of permanent, blistering daylight, while the other is a frozen wasteland of endless night. At first glance, this seems to rule out life, a world torn between two uninhabitable extremes. Yet, nature finds a way in the margins. Between these two hellscapes lies a narrow band of perpetual twilight called the Terminator. Here, the sun would forever sit on the horizon, a fixed, dim red orb that never rises or sets. Along this ribbon of land, temperatures could be mild and stable. Prevailing winds, driven by the immense temperature difference between the hot and cold sides, might circulate atmosphere and moisture, creating a band of potentially habitable real estate that wraps entirely around the globe. Life here would evolve under a sky forever painted in sunset hues. Plants, if they existed, might grow in a ring around the entire planet, their leaves perpetually angled toward the stationary sun. The concept challenges our Earth-centric view of a planet with global, uniform seasons. Teegardens Star B presents a different model for life, one confined to a linear oasis, a single, continuous coastline between two eternal oceans of fire and ice. It proves that a high Earth similarity index does not guarantee an Earth-like experience, but it does highlight a world where the fundamental conditions for liquid water, and therefore life as we know it, could be met in a most extraordinary way. The twilight band of Teegardens B is not alone in its star's gentle embrace. Orbiting the same faint sun is its sibling world, Teegardens Star C. This second planet also lies within the system's optimistic habitable zone, but it receives significantly less starlight, making it a colder, more enigmatic counterpart. If Teegardens B is a world of eternal sunset, then Teegardens C is a world of perpetual dusk, skirting the outer edge where warmth begins to fade. Its surface temperature, in the most optimistic models, might be similar to that of Mars, a frigid landscape where any surface water would likely exist as permanent ice. This presents a fascinating astrobiological possibility. A frozen surface does not necessarily mean a dead world. Beneath a thick, global ice shell, a vast subsurface ocean could be churned and warmed by two powerful forces. The first is geothermal heat, radiating from the planet's rocky interior, much like the oceans believed to exist beneath the icy crusts of Jupiter's moon Europa or Saturn's moon Enceladus in our own solar system. The second, more unique force could come from the star itself. Even a dim, cool star exerts a gravitational pull, and if Teegardens C's orbit is not perfectly circular, this constant tugging could flex the planet's interior. This process, called tidal heating, generates internal friction and warmth, potentially enough to keep a global ocean liquid for billions of years. So while Teegardens B offers the tantalizing prospect of a surface oasis along its terminator, Teegardens C whispers of a hidden, sunless sea. Life there would exist in perpetual darkness, not in a band, but potentially across an entire globe, thriving around hydrothermal vents on an alien seafloor, completely isolated from the dim red star above. Together, these two siblings present a stunning duality, one world where life might walk a razor's edge of twilight, and another where it could swim in a buried abyss, proving that within a single quiet star system, nature can draft two completely different blueprints for a living world. Hidden oceans might be the universe's most common cradles for life, and one world 120 light-years away has become the most famous example. K2-18b is a super-Earth, a world over 8 times more massive than our own, orbiting a cool red dwarf star. For years, its true nature was a mystery caught between two possibilities. Was it a mini-Neptune, a gaseous world with no solid surface, or something far more intriguing? Recent observations have tilted the scale dramatically toward a new and thrilling category, the hycean world. This term, a blend of hydrogen and ocean, describes a planet with a vast, global liquid water ocean beneath a thick, hydrogen-rich atmosphere. It is a world utterly alien to our experience, where the sky is not blue but a deep, hazy shade of purple or pink, and the atmospheric pressure at the ocean's surface would be crushing, hundreds of times greater than on Earth. Yet within that deep, dark sea, warmed from above by its star and from below by the planet's interior, the chemistry for life could thrive. The James-Webb Space Telescope turned its gaze to K2-18b, and what it found sent ripples of excitement through the scientific community. In the planet's atmosphere, Webb detected the clear signatures of carbon dioxide and methane. This combination is interesting, suggesting an active world, but the real shock came with a tentative, breathtaking hint of another molecule, dimethyl sulfide or DMS. On Earth, dimethyl sulfide is only produced by life, specifically by phytoplankton in our oceans. It is a robust biosignature, a chemical shout that biology is at work. The potential detection of DMS in the atmosphere of a hycean world is, without exaggeration, one of the most provocative findings in the history of exoplanet science. It suggests that in that global, pressurized ocean, something might be alive, but this is where caution is essential. The signal is faint, and scientists stress it is not yet a confirmation. Non-biological processes like exotic chemistry in a hydrogen-rich atmosphere or geological activity could potentially create similar signatures. The path forward is clear. Webb and future telescopes will stare at K2-18b again and again, gathering more light, refining the data, seeking to turn this tantalizing hint into a definitive detection. This world forces us to expand our imagination. Life does not need an Earth-like sky or a rocky shore. It could flourish in a planet-wide abyss under a smothering blanket of hydrogen and announce its presence with a gas we recognize from our own seas. K2-18b is no longer just an exoplanet. It is a question written in chemistry, hanging in a pink-hued sky over an alien ocean. The very structure of a hycean world defies our terrestrial intuition. Picture a planet where the sky is not a thin veil of nitrogen and oxygen, but a crushing planet-wide shroud of hydrogen gas hundreds of kilometers deep. Beneath this immense atmospheric blanket lies not continents, but a single, uninterrupted global ocean, so vast it could make Earth's Pacific seem like a pond. And at the very bottom of this alien sea, where pressures become almost unimaginable, the water itself may transform into exotic forms of high-pressure ice, creating a solid floor above the rocky mantle. This is the Hycean hypothesis in full, a model that turns K2-18b from a point of light into a layered, dynamic world. The hydrogen atmosphere acts as a powerful greenhouse, trapping enough of the star's faint warmth to keep the colossal ocean liquid even far from its sun. More importantly, that thick atmosphere provides a global shield against harmful radiation and cosmic rays, creating a stable, planet-wide environment for chemistry to unfold over eons. But could anything actually live in such a place? The answer may lie in the darkest depths of our own oceans. On Earth, we find entire ecosystems thriving around hydrothermal vents on the seafloor, places with no sunlight, crushing pressures, and water superheated by volcanic activity. The organisms there do not rely on photosynthesis, but on chemosynthesis, drawing energy from chemicals like hydrogen sulfide spewing from the Earth's crust. A hycean world's deep ocean could be peppered with similar vents on its rocky core, offering the same chemical energy buffet. Microbial life could originate there and over billions of years perhaps evolve into more complex forms, sustained by the nutrients circulating in the global current. The detection of potential biosignatures like dimethyl sulfide in K2-18b's atmosphere is so compelling precisely because of this model. In a Hycean scenario, life in the ocean would produce gases as byproducts, and those gases could slowly diffuse up through the water column and into the immense atmosphere, where our telescopes might eventually detect them. This redefines the cosmic hunt. We are no longer searching just for pale blue dots, for Earth twins with familiar shorelines and blue skies. We are now looking for pink-hued worlds with hidden global seas, understanding that the recipe for life might be brewing in pressure cookers we once thought were sterile. The Hycean hypothesis does not just add another candidate to our list, it explodes the list, opening thousands of previously overlooked worlds to serious consideration. Gazing up from a Hycean world's pink sky, the view is a solitary sun. But 23 light-years away, a planet offers a celestial spectacle unlike any other. GJ667cc orbits in a triple star system, a super-Earth where an observer might witness not one, but three suns hanging in the heavens. The primary star it circles is a faint red dwarf, part of a complex gravitational dance with two more orange dwarf stars further out. From the planet's surface, the primary star would appear large and dim, a deep crimson disk, while the two companion stars would shine in the sky like incredibly brilliant, multicolored point of light, casting faint, ever-shifting shadows. This world itself is a heavyweight, a super-Earth with a mass at least 3.5 times that of our own, suggesting a rocky composition with a far stronger gravitational pull. It completes a full orbit in just 28 days, sitting snugly within its red dwarf sun's habitable zone. But here lies a fascinating debate. This star is exceptionally metal-poor, meaning it contains very low amounts of elements heavier than hydrogen and helium. This affects the planet's formation and its potential climate. Some models suggest that despite being in the temperate zone, GJ667cc might actually be too cold for liquid water on its surface, more like a super-Mars than a super-Earth. Others argue that a thick carbon dioxide atmosphere could provide a powerful greenhouse effect, trapping enough heat to create a temperate environment. Its existence, regardless of the final verdict, is profoundly significant. It was discovered orbiting a star that astronomers once thought incapable of forming rocky planets, proving that nature is more creative than our theories. GJ667cc stands as a powerful symbol of abundance, demonstrating that potentially habitable worlds can emerge even in impoverished stellar environments and within complex multi-star systems. If life can gain a foothold here under multiple suns and around a star born from cosmic leftovers, then the galaxy may be overflowing with opportunities. 14 light-years from our solar system, a world called Wolf 1061c offers a stark lesson in cosmic real estate. This super-Earth, over 4 times the mass of our planet, sits squarely in the habitable zone of its quiet red dwarf star. Its incredible proximity makes it one of our closest known potentially habitable neighbors, a stone's throw in galactic terms. But location is everything, and this world occupies a perilous spot at the very inner edge of that temperate band. It receives about 65% more starlight than Earth does from our Sun. That seemingly small difference places it on a knife's edge between two destinies. With the right kind of atmosphere, one with moderate levels of greenhouse gases, Wolf 1061c could be a temperate, water-rich world. But with a thick, carbon dioxide-heavy shroud, it could easily tip into a runaway greenhouse effect, transforming into a hellish twin of Venus with surface temperatures hot enough to melt lead. This is the critical question that defines its potential for life. What is its air made of? The planet's fate, and the possibility of oceans or deserts on its surface, hinges entirely on the composition and thickness of its atmosphere. This makes it a prime target for the next generation of telescopes. Astronomers are eager to point instruments at Wolf 1061c to analyze the starlight filtering through its atmospheric veil during transits. They will hunt for the spectral fingerprints of water vapor, carbon dioxide, methane, and ozone. Finding a balanced mix could reveal a stable, Earth-like climate. Detecting an overwhelming blanket of carbon dioxide would tell a story of a world that lost its water long ago, a cautionary tale of a habitable zone gone wrong. Wolf 1061c is a reminder that being in the right neighborhood is only the first step. The true character of a world is written in the chemistry of its skies, a lesson we are now learning to read from across the light years. The delicate atmospheric balance of Wolf 1061c is a science of extremes, but some worlds hide their secrets beneath an impenetrable veil. 39 light-years away, GJ1214b presents a cosmic mystery that has both fascinated and frustrated astronomers for years. This planet is the archetype of a mini-Neptune, a world larger than Earth but smaller than the gas giants of our solar system. When the Hubble Space Telescope first tried to peer into its atmosphere, it saw nothing. The planet's spectrum was featureless, a bland, flat line that revealed no chemical fingerprints at all. This blank result was in itself a profound clue. It told scientists that GJ1214b is not shrouded in a clear, hydrogen-rich atmosphere like a typical gas planet. Instead, it is almost certainly enveloped in a thick, global layer of clouds or a high-altitude haze, a perpetual overcast so dense it completely obscures our view of the layers below. Imagine a world where the sky is not a window but a uniform, glowing white or gray ceiling, lit from behind by its dim red sun. This featureless shroud hints at a composition far stranger than simple gas. The leading theory paints a picture of a water world taken to an unimaginable extreme. Based on its mass and size, GJ1214b's interior is likely structured in layers. At its heart could be a solid, rocky and metallic core several times the mass of Earth. Surrounding that core, however, is not a mantle of rock but an ocean. But this is no ordinary sea. We are talking about a truly staggering volume of water, making up a significant fraction of the planet's entire bulk. The pressure in this deep global ocean would not be measured in Earth's atmospheres but in tens of thousands of them. Under such conditions, water behaves in alien ways. Closer to the core, the water is compressed into exotic forms of hot ice, like Ice 7 or Ice 10, crystalline structures that form under immense pressure even at searing temperatures. Above that, the water may exist as a supercritical fluid, a state that is neither liquid nor gas, but a bizarre, dense, fog-like substance with unique properties. Only in the uppermost layers beneath that global cloud deck might you find something resembling a traditional liquid ocean, but one under a crushing, opaque sky. GJ1214b is a reminder that some of the most common planets in our galaxy may be these enigmatic mini-Neptunes, worlds where the very concept of a surface dissolves into a gradual transition from thick atmosphere to deep, pressurized abyss. If life exists in such a place, it would be a chemistry thriving in perpetual twilight, under a blanket of clouds and within an ocean that defies all our terrestrial experience. 13 planets into our journey, we arrive at a world that checks nearly every box for a potential second Earth. TOI 700d is an Earth-sized planet discovered by NASA, a transiting exoplanet survey satellite, or TESS, orbiting a quiet red dwarf star 100 light-years away. What makes this planet so special is not just its size or its location in the habitable zone, but the remarkable tranquility of its sun. Unlike the violent, flaring red dwarfs we have encountered, TOI 700 is an M-dwarf star that has shown no signs of stellar flares in years of observation. This stability is a game-changer. A calm star means a stable energy output which allows for the possibility of a stable climate over billions of years. It gives a planet a fighting chance to develop and hold onto a protective atmosphere without having it constantly stripped away by radiation storms. This is the foundation upon which long-term habitability is built. Like many planets orbiting such stars, TOI 700d is almost certainly tidally locked, with one face in permanent daylight and the other in endless night. But advanced climate models have revealed a surprisingly hopeful picture. With a thick enough carbon dioxide atmosphere, global winds could efficiently redistribute the star's warmth from the hot day side to the frigid night side. This circulation could prevent the atmosphere from freezing out on the dark side and create a band of temperate conditions, particularly along the terminator line. Some models even suggest that with the right atmospheric pressure and composition, vast regions of the planet could maintain liquid water on its surface, not just in a narrow twilight strip, but across much of the sun-facing hemisphere. The possibility exists for a world with a giant, temperate ocean facing its star and a cold, icy cap on the far side. TOI 700d stands as a testament to careful discovery and optimistic modeling, a world where the pieces for a stable, watery environment align with a serenity rarely found around these common stars. But the story of the TOI 700 system grew even richer. In 2023, astronomers announced the discovery of a fourth planet, TOI 700e, another world orbiting within the star's habitable zone. This new world is slightly smaller than Planet D, about 95% the size of Earth, and it occupies an orbit between planets C and D. This placement is fascinating, as it means the star's temperate band is not home to just one promising world but two. Picture a solar system where two Earth-sized planets, TOI 700d and E, both circle their calm sun within the region where liquid water could exist. They are neighbors in cosmic terms, separated by a distance comparable to that between Mars and Jupiter in our own system. This configuration opens up a thrilling new line of thought. In a multi-planet habitable zone, the worlds are not isolated islands. They exist in a gravitational dialogue, their subtle tugs influencing each other's orbits over immense timescales. This interaction can stabilize their paths, preventing wild swings that might trigger extreme ice ages or hothouse periods. More speculatively, these neighboring worlds could share the ingredients for life. In the early, violent days of any planetary system, large impacts are common. A giant asteroid or comet striking one planet can blast debris containing water, organic molecules, or even hardy microorganisms into space. This material, traveling on a slow arc across the system, could eventually rain down upon the other world. This process, called panspermia, suggests that life might not have to originate independently on every promising planet. It could be seeded from a neighbor, a cosmic transplant carried on a rock. If TOI 700d developed a biosphere in its temperate ocean, a colossal impact could have sent fragments of its life bearing crust on a journey to TOI 700e. The two worlds, bathed in the same gentle starlight, could become siblings not just in orbit but in biology. This system challenges the idea of a single habitable world, offering instead a vision of a stellar oasis with multiple shores, where the story of life might be a shared one, written across the space between two pale dots of alien land. Buried in the old data from a retired telescope, a world was waiting to be seen. Kepler-186f is a story of human intuition triumphing over cold algorithms. After NASA's Kepler mission ended, scientists ran its vast datasets through automated programs designed to flag potential planets. One signal from a planet orbiting a quiet red dwarf star 300 light-years away was dismissed by the computers as a false positive, just noise in the numbers. But a team of volunteer citizen scientists, part of the Kepler False Positive Working Group, decided to take a closer look. Scrolling through the light curves themselves, they spotted the subtle, repeating dip in starlight that the machines had overlooked. Their discovery revealed a world almost exactly the same size as Earth, a rocky twin receiving about 75% of the stellar energy our planet gets from the Sun. This places it firmly within its star's conservative habitable zone, a region where liquid water could exist with the support of a modest atmosphere. The planet's orbit takes just 19.5 Earth days, a fleeting year under a dim, crimson sun. The rediscovery of Kepler-186f sent a ripple of profound excitement through the astronomy community. It was not just the planet itself, though its Earth-like metrics are compelling. It was the powerful implication that our best automated tools are still imperfect. If a world this promising could be hiding in plain sight within data we had already collected, what else might we have missed? This single point of light, rescued by diligent human eyes, became a symbol of renewed hope. It suggested that the census of habitable worlds in our galaxy, already thought to be in the billions, might be even larger. Every unexamined dataset, every overlooked signal, could hold another Earth-sized world circling patiently in the gloom. Kepler-186f is more than an exoplanet. It is a promise and a cautionary tale. It promises that the cosmos is generous with its real estate, offering second chances even in old data. And it cautions us that the final map of our living galaxy will not be drawn by machines alone, but by the relentless curiosity of people who still believe there are wonders left to find. Kepler-452b was a landmark discovery that captured the world's imagination. Announced in 2011, it was the first planet found by the Kepler telescope to orbit comfortably within the habitable zone of a Sun-like star. That single fact, beamed back from 600 light-years away, felt like a revelation. Here was a world about 2.4 times the size of Earth, circling a star remarkably similar to our own, with a year of 290 days. The light from its sun on an alien surface would feel familiar, a gentle yellow-white glow. But for all its promising location, Kepler-452b remains an enigma wrapped in a tantalizing distance. Its size places it directly on the boundary between two radically different planetary families. It could be a super-Earth, a massive rocky world with a solid surface, perhaps covered in a global ocean. Alternatively, it might be a mini-Neptune, a gaseous world with a thick, deep atmosphere and no definable surface at all, just layers of increasingly dense and hot gas merging into a slushy, high-pressure interior. We simply do not know which version of this world is real. That fundamental uncertainty is a perfect snapshot of where exoplanet science stood in its early days and the long road we have traveled since. Kepler gave us the gift of location, proving that planets like this existed in the temperate zones of friendly stars, but it could not tell us their true nature. Was Kepler-452b a water world with endless seas under a blue sky, or a shrouded gas ball with crushing pressures and no shore to stand on? This question has fueled over a decade of scientific debate and modeling. If it is rocky, its greater mass would mean stronger gravity and a potentially thicker atmosphere, which could make it a super-habitable world, more geologically active and better at holding onto its oceans. If it is gaseous, any hope for surface life as we know it vanishes, though the possibility of aerial life in its upper cloud decks remains a distant, speculative thought. Kepler-452b stands as a monument to a pivotal moment, the first confident step into a galaxy we now know is teeming with possibilities. It taught us to ask the next harder question, not just is it in the right place, but what is it actually made of? The question of what a world is made of leads us to a star 42 light-years away, where a super-Earth named HD 40307g offers a different kind of stability. Orbiting an orange dwarf star slightly smaller and cooler than our Sun, this planet is a heavyweight with a mass at least 7 times that of Earth. Its orbit places it squarely in the middle of its star's habitable zone, and it takes about 200 days to complete a leisurely year. This orbital distance is a significant advantage. Being further out from its star than many of the red dwarf worlds we have discussed, HD 40307g is less likely to be tidally locked. It could rotate on its axis much like Earth does, giving it a normal day-night cycle with familiar sunrises and sunsets. This rotation promotes a more even distribution of heat and encourages complex weather patterns, which are crucial for maintaining a stable, global climate over geological timescales. With a potentially thick atmosphere and the right mix of greenhouse gases, this world could be a truly temperate super-Earth, perhaps covered in vast, shallow seas or sprawling continents under an orange-tinted sky. But the true wonder of HD 40307g is not its solitude but its company. It is not a lone world circling its star, but one of at least 6 planets in a complex, tightly packed system. All 6 worlds orbit closer to their star than Mercury does to our Sun, yet because the star is dimmer, several of them, including planet G, reside in that temperate zone. This compact architecture defies the classic model of our own solar system, where planets are widely spaced. It suggests a completely different story of formation, where the protoplanetary disk around this star was rich in material and the planets migrated into a delicate, resonant dance. A multi-planet system like this one is a crucible for diversity. The gravitational interactions between these close siblings can stir their interiors, driving geological activity like volcanism and plate tectonics, processes that are vital for recycling nutrients and regulating a planet's atmosphere through the carbon cycle. The presence of so many neighboring worlds also increases the chance of material exchange through impacts, potentially seeding similar chemistries across the system. HD 40307G presents a vision of cosmic community, a world whose very potential for habitability may be deeply intertwined with the gravitational push and pull of its planetary family, reminding us that a living world might often be born from celestial conversation, not isolation. Only 11 light-years from our solar system, Ross 128b orbits one of the quietest red dwarf stars we have ever found. This stellar serenity is its greatest gift. While other red dwarfs erupt in flares that can sterilize their planets, this star is a picture of cosmic calm, offering its world a stable, gentle light for billions of years. The planet itself is a super-Earth with about 1.3 times our mass, and it receives only 38% more stellar radiation than Earth does. This places it at the warmer edge of its star's habitable zone, suggesting a climate that could be temperate, perhaps even balmy, if it possesses an atmosphere similar to our own. Surface temperatures in the most optimistic models might average around a comfortable 70 degrees Fahrenheit. Imagine a world where the risk of a stellar storm stripping away the sky is almost non-existent, where the sun is a fixed, deep red ember in a perpetual twilight sky, and the conditions for chemistry have been undisturbed for eons. This combination of proximity and peace makes Ross 128b a jewel in the crown of nearby exoplanets. Its tranquil star does more than just nurture potential life. It offers astronomers an unprecedented opportunity. A calm stellar environment means the planet's own light is not drowned out by violent stellar activity. Future telescopes like the planned Habitable Worlds Observatory could one day attempt to directly image this world to capture its pale dot of reflected light separate from the glare of its star. From that faint gleam, we could analyze its spectrum in exquisite detail, searching for the telltale signs of oxygen, water vapor, methane, and other gases that would paint a portrait of its air and surface. Ross 128b represents a future milestone, a nearby world where the cosmic noise fades into silence, giving us our clearest chance yet to listen for the chemical whispers of another living world. The search for a living world is a story of both discovery and doubt. 20 light-years away, a scientific saga unfolded around a star called Gliese 581, a quiet red dwarf that seemed to host a family of planets. In 2010, a team of astronomers announced a stunning find, Gliese 581g, a world with about 3 times the mass of Earth, orbiting squarely in the middle of its star's habitable zone. The data suggested it was a rocky super-Earth, and with its location, it was immediately hailed as one of the first and most promising candidates for a potentially habitable exoplanet. The possibility was intoxicating. Here was a world that could have liquid water, a stable climate, and the right conditions for chemistry to flourish, all within our cosmic backyard. Given its tight orbit around a red dwarf, scientists assumed it would be tidally locked, presenting the now familiar model of a world with a scorching day side, a frozen night side, and a narrow, temperate ribbon of twilight in between. For a moment, it felt like a definitive answer was within reach, but science is a self-correcting process, and the story of Gliese 581g took a dramatic turn. Other research teams revisited the same data, applying different analytical techniques to disentangle the subtle gravitational tugs of the multiple planets in the system from the natural noise of the star itself. Their conclusions were sobering. They could not confirm the planet's signal. The wobble in the starlight attributed to Gliese 581g, they argued, was not caused by a new world but was actually a complex artifact, a statistical mirage produced by the combined signals of the other known planets and the star's own activity cycles. The astronomy community became divided, with some defending the original detection and others dismissing it entirely. For over a decade, the planet has existed in a state of limbo, neither confirmed nor entirely ruled out, its name often carrying an asterisk in scientific literature. This controversy is not a failure, but a vital lesson in the rigorous, painstaking nature of exoplanet science. Detecting these distant worlds is an exercise in extreme precision, akin to trying to hear a whisper in a hurricane. The methods we use, like the radial velocity technique that found Gliese 581g, involve measuring minute changes in a star's light. Sometimes, the signal of a planet is so faint it blends with the natural pulsations and magnetic storms on the star's surface. Disentangling truth from illusion requires multiple observations, independent verification, and often years of patient follow-up. Gliese 581g stands as a monument to scientific caution. It reminds us that every exciting claim must weather the storm of scrutiny, and that the path to truth is paved with both brilliant insights and healthy skepticism. The dream of a habitable world around Gliese 581 may still be out there, waiting for more powerful tools to either reveal it or finally lay it to rest, teaching us that in the hunt for other Earths, the questions we ask are just as important as the answers we think we find. The debate over Gliese 581g exposes a deeper truth about our search for life. For decades, the concept of the habitable zone has been our guiding star, that narrow band around a sun where temperatures are just right for liquid water to pool on a planet's surface. We call it the Goldilocks zone, not too hot, not too cold, but just right. This simple idea has been incredibly powerful, giving us a clear place to start looking. But the universe is rarely simple. The very boundaries of this zone are not fixed. They shift dramatically depending on the star at the center. A hot, massive blue giant star has a habitable zone that is staggeringly far out, while a cool, tiny red dwarf's temperate band hugs it so closely that a year there can be just a few Earth days. This means a planet in the zone of a red dwarf faces intense tidal forces and radiation that a planet in a sun-like star's zone does not. More importantly, the classic habitable zone model makes a critical, Earth-centric assumption that life requires a sunlit surface ocean. This is where our imagination must expand beyond the textbook diagram. Consider our own solar system. Europa, a moon of Jupiter, lies far outside the Sun's traditional habitable zone in the deep freeze of the outer solar system. Its surface is a global, icy shell. Yet beneath that ice, scientists are confident of vast, salty ocean churns kept liquid not by sunlight, but by the gravitational flexing of Jupiter's immense pull. This tidal heating creates a subsurface habitable zone, a world of liquid water isolated from the surface, powered by geology and gravity rather than starlight. Enceladus, a small moon of Saturn, jets plumes of that subsurface ocean into space from cracks in its icy crust, offering us a direct sample. If life can exist in these dark, sunless seas next door, then why not on an exoplanet with a similar setup? A frozen super-Earth orbiting a dim star or a distant moon around a gas giant could harbor a warm ocean beneath miles of ice. Their address in the galaxy would be all wrong according to the old map, but they could be teeming with chemistry. This forces us to redraw the map of possibility. Habitability is not just about a planet's distance from its star. It is about the total energy budget available to keep water liquid. That energy can come from starlight, yes, but it can also come from a planet's own hot core, from the radioactive decay of elements in its mantle, or from the relentless gravitational kneading of a nearby giant world. A tidally heated planet, stretched and compressed by its orbit, could be warm and active, even drifting alone in the cold dark between stars. The story of Gliese 581g, whether it is real or a mirage, ultimately points us toward a more profound realization. We are not just hunting for planets in a zone. We are hunting for worlds with the right internal fire, the right gravitational relationships, the right chemistry to nurture a spark. The true habitable zone may not be a circle around a star, but a hidden, liquid layer deep inside 1,000 different kinds of worlds. Clouds are not just weather, they are planetary thermostats. 36 light-years away, a super-Earth named HD 85512b demonstrates this delicate balance with stunning clarity. This world, about 3.5 times the mass of our own, orbits an orange dwarf star. Its position is precarious, sitting at the very inner edge, the warmer boundary, of its star's habitable zone. It receives significantly more stellar energy than Earth does, which should, in theory, make it far too hot for liquid water. Early climate models painted a picture of a Venus-like hothouse, but then scientists introduced a single, crucial variable, clouds, when they ran simulations assuming HD 85512b had an Earth-like atmosphere and a cloud cover of at least 50%, the results transformed. Those bright, reflective clouds acted like a global sunshade, bouncing a substantial portion of the incoming starlight back into space before it could heat the surface. This cooling effect was enough to tip the scales, potentially creating pockets where temperatures could allow for liquid water to exist, particularly in the planet's higher latitudes or on its night side if it is tidally locked. This is the power of planetary albedo, a measure of how much light a world reflects. A planet with bright white clouds or icy polar caps has a high albedo, staying cooler. A world with dark oceans or vast basalt plains absorbs more heat, growing warmer. HD 85512b's hypothetical habitability hinges entirely on this reflective shield. It forces us to consider that a planet's color and cloud composition are not minor details, but primary determinants of its fate. An otherwise identical planet with darker clouds or fewer of them would boil away its oceans. This super-Earth teetering on the edge shows us that climate stability is an active, dynamic process. It is not a fixed setting, but a constant negotiation between the heat coming in and the light reflected back, a negotiation where clouds hold a decisive vote. That delicate balance of clouds and climate finds a more serene expression 1,200 light-years away. Kepler-62f is a world that embodies the classic dream of a habitable planet. It is a super-Earth about 40% larger than our own, orbiting a star significantly cooler and dimmer than our Sun. This places it in the outer region of the star's habitable zone, a position that would typically suggest a colder, perhaps frozen world. Yet its distance from its gentle sun is precisely what makes it so compelling to climate scientists. Because it receives less stellar energy, Kepler-62f would need the help of a greenhouse atmosphere to maintain liquid water. But unlike a planet on the inner edge, where too much greenhouse gas leads to a runaway inferno, this world has room to breathe. Advanced climate simulations have explored a wide range of possibilities for its atmosphere. The results are remarkably optimistic, with an atmosphere rich in carbon dioxide at pressures anywhere from the same as Earth's up to 5 times thicker, and with a modest amount of cloud cover, Kepler-62f could easily maintain a stable, global temperature above freezing. Some of the most detailed models suggest it is not just habitable, but a true water world, a planet almost entirely covered by a global ocean, with perhaps only chains of volcanic islands or small continents breaking its endless surface. The consistency of these models across different assumptions is what gives astronomers such confidence. This isn't a world balanced on a knife's edge. It is a world with a wide, stable plateau of possible climates that could support liquid water for billions of years. The star itself, a quiet K-dwarf, offers a longevity and stability that our own Sun will eventually lose. Standing on a rocky shore of Kepler-62f, you would look out across a deep, alien sea under a soft orange sky. The waves would be driven by tides from its neighboring planets, and the climate would be temperate, moist, and remarkably steady. It is a vision of planetary serenity, a world where the chaos of formation has settled into a lasting, nurturing calm, offering the time and stability that life on Earth used to flourish. The world of Kepler-62f may not be alone in its watery serenity. Orbiting closer to the same gentle star is its sibling, Kepler-62e, a super-Earth about 60% larger than our planet. This world basks in a warmer embrace, receiving about 20% more starlight than Earth does, placing it comfortably in the inner part of the habitable zone. While Kepler-62f might be a cool, global ocean with scattered islands, its closer sibling likely experiences a more tropical climate. Imagine Kepler-62e as a true water world, its entire surface a deep, warm, and possibly shallow sea with no land in sight. The sky here would be a deeper shade of orange, and the ocean currents, driven by the star's stronger heat, would be powerful and planet-spanning. This presents us with a stunning cosmic diptych, two sibling worlds, both likely drowned in global oceans, but existing at different temperatures within the same star's nurturing light. One is a cooler, perhaps deeper abyss, the other a warmer, more energetic sea. The existence of two such worlds in a single system forces a thrilling line of speculation. Could life arise independently in both of these alien oceans? The ingredients would be similar, bathed in the same starlight, but the environments would differ. Life in the warmer seas of Kepler-62e might evolve faster, its biochemistry tuned to a different thermal rhythm. Meanwhile, in the cooler, darker depths of Kepler-62f, life might take a slower, more deliberate path. But there is another, even more intriguing possibility. In a young planetary system, giant impacts are common. A colossal asteroid strike on Kepler-62e could blast fragments of its ocean, teeming with microbial life, into space. These rocky life rafts, encasing hardy organisms, could travel the relatively short distance across the system on a slow trajectory, eventually falling as meteorites into the global ocean of Kepler-62f. This process, called panspermia, suggests the two worlds might not develop life separately but share it. A microbe that evolved in a warm, shallow sea could find a new home in a cool, deep abyss, seeding a second genesis with a shared family tree. The Kepler-62 system offers a profound vision, not of a single oasis but of a stellar archipelago where the story of life might be written not on one world but exchanged between two, carried on stones between twin seas. A mere 12 light-years away, a star almost indistinguishable from our own Sun shines in the constellation Cetus. Tau Ceti is a yellow dwarf, a near twin to the star that warms our planet, and orbiting within its glow is a world of extremes, Tau Ceti-e. This super-Earth, with a mass at least 4 times our own, occupies a perilous and pivotal spot. It circles on the very inner edge of its Sun's habitable zone, a placement that makes its nature a matter of intense debate. With the intense stellar energy it receives, this world could easily be a scorching, Venus-like inferno, its surface hot enough to melt metal, any ancient oceans long since boiled away into a thick, suffocating atmosphere. Yet, with just the right atmospheric composition, perhaps one with reflective clouds and limited greenhouse gases, it could, in theory, maintain temperate conditions. The possibility, however slim, of a habitable world around a sun-like star so close to us is electrifying. But Tau Ceti's environment may be shaped by a far more violent factor than its proximity to its star. Astronomers have detected a massive debris disk swirling around Tau Ceti, a sprawling belt of comets, asteroids, and dust far more dense and massive than the one in our own solar system. This is not a serene, orderly system, it is a cosmic shooting gallery. The presence of such a dense disk implies a history of colossal collisions and a present-day reality of frequent, devastating impacts. For any emerging life, this is a double-edged sword. On one hand, a constant barrage of giant asteroids would be an existential threat, capable of sterilizing the planet's surface repeatedly, resetting the clock on evolution just as it begins to tick. A civilization, if one ever arose, would live under the perpetual shadow of extinction-level events. Yet, on the other hand, these same impacts are the delivery vehicles for the essential ingredients of life. Icy comets and water-rich asteroids from that very disk could have been the source of Tau Ceti's oceans, if it has any. They carry the complex organic molecules, the amino acids and probiotic chemicals that are the building blocks of biology. In this violent paradox, the same force that could wipe out a biosphere may also be the one that seeded it in the first place. Tau Ceti presents us with a brutal equation. Can life arise and persist fast enough and become resilient enough to survive the very bombardment that gave it its start? It is a world where existence would be a relentless race between creation and catastrophe. While Tau Ceti simmers on the inner edge, its sibling world, Tau Ceti F, offers a completely different story. Orbiting much farther from their shared sun, this super-Earth exists in a colder, more distant region of the system. The starlight reaching Tau Ceti F is faint, only a fraction of what Earth receives, placing it in the outer reaches of the star's habitable zone. At first glance, this suggests a frozen wasteland, a super-Earth locked in a global ice age, its potential for life entombed beneath miles of glacial crust. But the surface temperature of a planet is not dictated by sunlight alone. The internal heat of a world, the radioactive warmth from its core, can be a powerful engine. If Tau Ceti F is geologically active, with a hot interior churned by the gravitational tides of its star and neighboring planets, that heat could radiate upward, creating pockets of liquid water beneath the ice. We see this principle at work in our own solar system on moons like Europa and Enceladus, where subsurface oceans thrive in total darkness, warmed solely by gravitational squeezing. Tau Ceti F, with its greater mass and likely rocky composition, could be a scaled-up version of these icy moons, a frozen shell hiding a global dark sea. There is another possibility. A thick, insulating atmosphere rich in greenhouse gases like methane could wrap the planet in a thermal blanket, trapping enough of the feeble starlight to raise surface temperatures above freezing. This would transform it from an ice world into a cold but potentially habitable super-Earth with liquid water on its surface, perhaps in the form of a global, slushy ocean under a dim, yellow sky. The stark contrast between the two worlds is a lesson in cosmic diversity. In a single star system, we find two potential super-Earths, one, Tau Ceti, battling intense heat and bombardment at the inner edge, and the other, Tau Ceti F, confronting profound cold at the outer boundary. They represent opposite solutions to the puzzle of life, one possibly relying on reflective clouds to cool down, the other on internal fire or a thick atmosphere to warm up. This duality forces us to ask whether a single stellar family can nurture life in more than one way, or if these two siblings represent bookends with the true sweet spot lying silently between them, waiting to be discovered. The sibling worlds of Tau Ceti present a study in extremes, but our closest stellar neighbor holds another, even smaller secret. Proxima-Centauri-d is the lightest exoplanet ever discovered using the radial velocity method, a world with a mass barely a quarter of Earth. It is a whisper of a planet, a tiny, swift companion to the red-dwarf star just 4.2 light-years away. This world completes a frantic orbit in a mere 5 Earth days, skimming so close to its temperamental sun that its surface, if it has one, is likely scorching hot. The environment here is brutal, bathed in intense radiation from Proxima Centauri's frequent stellar flares. This proximity and punishment raise a critical question. could such a small, fragile world hold onto anything resembling an atmosphere? With its low mass, its gravity is weak, making it extraordinarily difficult to retain gases against the relentless stellar wind. Many scientists believe Proxima-Centauri-d is likely a bare, airless rock, a charred and silent place where the concept of a sky has been stripped away by its own sun. Yet its very existence is profoundly significant. Its discovery, confirmed in 2020, revealed that our nearest star system is not just home to the promising Proxima-Centauri-b, but to at least 3 known planets. This compact family, a potentially habitable world, a colder super-Earth, and now this tiny, scorched inner sibling paints a picture of a complex, multi-planet system packed into a space smaller than Mercury's orbit in our solar system. Proxima-Centauri-d, for all its likely barrenness, teaches us that these dense, populous planetary arrangements may be the rule, not the exception, especially around the galaxy's most common stars. It suggests that where one promising world is found, others often follow, a cosmic principle of abundance that turns every flickering red dwarf into a potential hub for hidden worlds. The crowded neighborhood of the TRAPPIST-1 system holds more than just its crown jewel. Orbiting closer to the dim red sun are 2 sibling worlds, TRAPPIST-1c and 1d, that demonstrate just how thin the line is between a living world and a dead one. The innermost of these, Planet C, is a stark warning. It is a world almost exactly the same size and mass as Earth, but it circles its star in a blistering 2.5 days. At that distance, the feeble red sunlight still delivers a devastating punch, likely heating the surface to hundreds of degrees. Scientists believe TRAPPIST-1c is a textbook example of a runaway greenhouse effect. Any water it once possessed would have long since boiled away into the upper atmosphere, where ultraviolet light from the star could split the water molecules, allowing the lightweight hydrogen to escape into space forever. What remains is probably a scorched, bone-dry rock shrouded in a thick, suffocating atmosphere of carbon dioxide, a perpetual pressure cooker under a crimson sky. It is a Venus in miniature, a haunting portrait of what happens when a planet slips too close to the fire, a fate that could have befallen Earth had our orbit been just a little tighter. Its immediate neighbor, TRAPPIST-1d, tells a more nuanced and hopeful story. Slightly smaller and cooler, it orbits just far enough out to straddle the very inner edge of the system's habitable zone. This placement puts it on a climatic knife edge. The starlight it receives is still intense, but not necessarily fatal. The difference between a Venus-like inferno and a temperate, water-bearing world could come down to the composition of its air. If TRAPPIST-1d has a moderate atmosphere with reflective clouds, it could bounce enough heat back into space to keep global temperatures in check. Some climate models suggest it might even host a global ocean, though one that would be perpetually steamy and warm. Other models, however, show it tipping over into the same runaway greenhouse state as its sibling. The key variable is the amount of carbon dioxide. Too much, and the greenhouse effect runs wild, trapping all the incoming heat and boiling the oceans. Just enough, combined with water clouds and a stable climate, becomes possible. These 2 worlds, C and D, are cosmic twins born from the same disk of material, yet they may have diverged onto utterly different paths because of a slight difference in distance and atmospheric history. They are a paired lesson in planetary fate, showing us that in the delicate balance of a solar system, the margin between a hellscape and a haven can be as narrow as the space between 2 orbits. Moving outward from that delicate inner edge, the TRAPPIST-1 system reveals its full, breathtaking architecture. Beyond the scorched rock of Planet C and the knife-edge world of Planet D, beyond the oceanic jewel of Planet E, lie 3 more siblings, the outer trio of F, G, and H. Planets F and G are both firmly within the star's habitable zone, receiving starlight comparable to what Venus and Mars get from our Sun, respectively. This places them in a fascinating position. TRAPPIST-1F, slightly cooler than Earth, could be a world where water exists largely as ice, but with a thick enough atmosphere to trap heat, or with the internal warmth of tidal forces, its frozen shell might give way to pockets of liquid water, perhaps a slushy global ocean. Its neighbor, TRAPPIST-1G, is larger and more massive, a super-Earth that might hold onto a substantial atmosphere. The conditions here could allow for open water, a true blue, or rather crimson, mar under its dim sun. These are not mere specks of light, they are two additional chances for biology in a single backyard solar system. Then there is the outermost known member, TRAPPIST-1H. This small, distant world skirts the outer fringe where sunlight is feeble. It is likely an icy snowball, a frozen sentinel at the system's edge. Yet even here, the story may not be over. The extraordinary compactness of this family is the source of its greatest wonder. All 7 planets orbit closer to their star than Mercury does to our Sun. This proximity creates a gravitational symphony. As these worlds swing past each other in their precise, resonant orbits, they pull on one another with gentle but persistent tugs. This gravitational dance does 2 remarkable things. First, it can squeeze and flex the planet's interiors, generating tidal heating. This internal warmth could keep subsurface oceans liquid even on the colder outer worlds, turning a frozen ball like TRAPPIST-1H into a candidate for a hidden, sunless sea. Second, these mutual tugs provided the key to their discovery. Astronomers didn't just see the planets dim their stars' light, they noticed the transits happening slightly early or late. These transit timing variations were the fingerprints of gravitational interaction, allowing scientists to weigh the planets and confirm this was not a false signal, but a true family of worlds gently nudging each other in the dark. This intricate clockwork reveals a system where the planets are in constant, silent conversation, their fates intertwined by gravity, offering not one, but multiple canvases where the chemistry of life might have begun to paint. A world's true potential is measured by more than its place in the sky. Kepler-452b, orbiting over 1,000 light-years away, scores a remarkable 0.84 on the Earth Similarity Index, placing it among the most Earth-like worlds we have ever catalogued. It is a super-Earth about 1/3 larger than our planet, and it basks in the gentle, orange-tinted light of a K-dwarf star. This stellar category, often called an orange dwarf, represents a crucial middle ground in the cosmic search for life. They are smaller, cooler, and longer-lived than stars like our Sun, yet they are far more stable and serene than the volatile red M-dwarfs that host so many of our other candidates. A K-dwarf star can shine steadily for tens of billions of years, offering a calm, consistent source of energy to any orbiting planets. This longevity is a gift of almost unimaginable scale. On Earth, it took roughly 4 billion years for simple single-celled life to evolve into the complex, multicellular organisms we see today. That is nearly the entire current lifespan of our own Sun. A planet around a K-dwarf, however, is granted a timeline that could be twice as long or more. This provides an evolutionary runway of epic proportions, granting biology not just millions, but extra billions of years to experiment, adapt, and complexify. The environment is also gentler. K-dwarfs emit less of the high-energy ultraviolet radiation that can damage complex molecules and strip away atmospheres, compared to both hotter Sun-like stars and flaring red dwarfs. This combination of stability, longevity, and a milder radiation environment has led many astrobiologists to propose that K-dwarf stars might be the true Goldilocks stars for complex, advanced life. They are not too hot, not too cold, not too violent, and they shine for a very, very long time. Kepler-452b, nestled in the habitable zone of such a star, could be a world with a deep, stable climate, perhaps with continents and oceans that have persisted for longer than Earth has even existed. If life arose there, it has had the one ingredient we know is essential for intelligence: deep, uninterrupted time. Standing on its surface, the Sun would appear larger and more orange in the sky, casting a perpetual amber glow over landscapes that have known only gradual change for eons. This world asks us to reconsider our stellar chauvinism. Perhaps we do not orbit the ideal star for life. Perhaps the most promising homes for civilization are not under yellow suns like ours, but under the enduring, gentle light of an orange star, where time itself is the greatest asset a living world can possess. Kepler-452b is a story of hope followed by a sobering cosmic lesson. This world, discovered in 2015, seemed to be everything we were searching for. It was an Earth-sized planet, only 12% larger than our own, orbiting comfortably within the habitable zone of its star. Its Earth Similarity Index score was remarkably high, making it one of the most promising twins to our world we had ever found. For a moment, it felt like a definitive answer, a rocky world bathed in the right amount of light where oceans could lap against alien shores. But the star at the center of this hopeful system is a red dwarf and not a gentle one. Kepler-452 is a tempest. Observations revealed that this star unleashes catastrophic superflares, monstrous outbursts of energy that dwarf anything our Sun has ever produced. These are not mere solar flares, they are stellar tantrums of apocalyptic scale. A single superflare from Kepler-452 could release energy equivalent to 100 billion megatons of TNT, enough to strip away a planet's atmosphere in a series of violent blasts. The radiation accompanying such an event would scour the surface, breaking apart complex molecules and sterilizing any emerging biology. This devastating reality transformed Kepler-452b from a prime candidate into a cautionary tale. It sits perfectly in the Goldilocks zone for temperature, but it orbits within a zone of stellar fury that makes long-term habitability nearly impossible. The planet's story forces us to refine our search parameters dramatically. A planet can have the perfect size, the perfect orbit, and the perfect composition, but if its Sun is a violent, unstable parent, all of that potential can be erased in an instant. Kepler-452b stands as our 30th and final world on this journey, a poignant reminder that the cosmic checklist for life is longer and more demanding than we once thought. It is not enough to simply be in the right place. A living world needs a stable, nurturing star, one that offers not just light but also peace. Kepler-452b's harsh fate refines the very question we ask. Our list of 30 is not a final catalogue but a starting point, a snapshot of possibility taken with the tools of one moment in time. The true revolution is not just in finding these worlds but in learning to read them. The James-Webb Space Telescope is now our most powerful interpreter, using a technique called atmospheric spectroscopy. When a planet transits its star, a tiny fraction of that starlight filters through the planet's thin atmospheric veil. Webb's exquisite instruments can spread that light into a rainbow, a spectrum. Within that spectrum are dark lines like a chemical barcode. Each line corresponds to a specific molecule absorbing light. Webb is not just looking for water vapor or carbon dioxide anymore. It is hunting for chemical combinations that defy simple geology. One of the most tantalizing is methane disequilibrium. In an atmosphere with oxygen like Earth's, methane is a fragile molecule that should quickly break down. Finding a lot of it means something must be constantly replenishing the supply. On our planet, that something is overwhelmingly life, from microbes in wetlands to the digestive systems of animals. Detecting methane alongside other gases like carbon dioxide without an abundance of carbon monoxide could be a powerful biosignature, a sign of an active biosphere at work. This search will soon leap forward again. Planned missions like the Habitable-Worlds Observatory aim to do what no telescope has done before: directly image an Earth-like planet around a Sun-like star as a distinct pale blue dot separate from the glare of its Sun. From that single point of light, we could analyze its global spectrum, mapping continents and oceans, seasons and weather, and reading the composition of its air with unprecedented clarity. We are also expanding our definition of a signal. The search for biosignatures, signs of life's chemistry, is now joined by the hunt for technosignatures, signs of technology. This includes looking for artificial lights on a planet's night side, industrial pollutants like chlorofluorocarbons in an atmosphere, or even the structured radio whispers of communication. These are long shots, but they acknowledge a profound idea. If a biosphere can alter a world's chemistry, a civilization could alter its light. So this list of 30 is a beginning, not an end. Every new telescope, every refined technique, every night of observation adds new names and crosses others off. Some of these worlds will be revealed as barren, while others, currently unknown, will emerge from the darkness into the spotlight of promise. The journey from a flicker of starlight to a world with a name, and perhaps one day a story of its own, is the greatest detective story ever told. We are learning the language of planets, and we have just begun to listen. From global oceans under pink skies to frozen worlds with hidden seas, the sheer diversity is staggering. We have journeyed to planets gripped by eternal twilight, super-Earths warmed by internal fire, and hycean worlds where life might announce itself with a gas from our own oceans. Each of these 30 exoplanets represents a different answer to the same profound puzzle, a unique combination of starlight, gravity, chemistry, and time that could, against all cosmic odds, nurture a spark. The question of whether we are alone is not answered by a single discovery, but by this growing mosaic of possibility. Every point of light on this list, from our nearest neighbor Proxima-Centauri-b to the distant water world Kepler-62f, chips away at our isolation. They transform the universe from a silent, empty void into a neighborhood of potential, each world a chapter in a story we are only beginning to read. This search does more than catalog planets, it redefines our place in the cosmos. We are no longer just inhabitants of a solitary pale blue dot. We are the conscious part of a universe becoming aware of its own fertility. So the next time you look up at the night sky, remember that the darkness between the stars is not empty. It is filled with whispers of pink-hued atmospheres, the slow churn of alien oceans, and the quiet, patient chemistry of a billion other shores. The greatest discovery in history still awaits, and it is written in the light of a distant sun, waiting for us to understand its message. Stay curious.